Hi everyone, and thank you for joining. In this lesson, we'll discuss the differentiability of a function. Differentiability has the roots on the word derivative. To find the derivative of a function means to differentiate it. If a function can be differentiated, then we say it is differentiable. So that's what we're discussing today. So the differentiability or the ability to be differentiated. Now, you're probably wondering, what's a differentiability story? So aren't all functions differentiable? Well, in order to understand this, we're going to go back to the definition of the word derivative. So we say that derivative means to find the speed of change of the y values, or in other words, the instantaneous rate of change of a function, or the y values of a function. And we found that by measuring the slope of the tangent line drawn on the graph of a function. So now we're thinking that in order to find the derivative, it means that we need to be able to draw the tangent line, measure the slope, and that would be the derivative. So the question I'm posing here is a function, if a function is undefined at a point, can we draw a tangent line at points where when a function is undefined? So think about graphs that showed just jump discontinuities or holes or equations of functions with restrictions. So we're going to say that if a function is undefined at a point, then we cannot draw a tangent line. And obviously, if we cannot draw the tangent line, then we cannot measure the slope of a tangent that doesn't exist. So therefore, the condition 1 for differentiability is that the function is continuous at a point in order to be able to draw the tangent, find the slope of the tangent, thus the derivative of the function. So as an example here, I brought in the example of a graph where you can see how we find the derivative of a function graphically. We draw a tangent at a point where we're measuring the speed of change of y values, measure the slope of it, and the slope would be the derivative of the function. Now, there are occasions though where the graph, let's say for example, if the graph had a hole in here, we're unable to draw a tangent line because the tangent line has to touch the graph at a point, and if the point is empty, so if there is no graph, we cannot draw a tangent. Now, the second scenario that I want us to discuss, or I want to bring here, is cases where we can draw a tangent line, however, we cannot measure the slope of it. If we cannot measure the slope of a tangent line, it means we cannot measure the derivative of it. So remember that tangent lines are straight lines. Can you draw a line with an undefined slope, which means that the derivative would be undefined? So I would say, oh yes, I remember some of them. So, and what type of line would this be? I'm going to bring as examples here, this line here. So that's a straight line. It seems that the slope is measurable and the slope is positive, which means that the derivative here, if this was to be the tangent on the graph of some function f, the derivative of it at that point must be positive. This tangent line drawn at some function, at some point on a function f, seems to have a negative slope, which means that the derivative has to be negative. Now, if the tangent line happened to be horizontal line, that means that the slope of it, or the rate of change of this tangent line, will be 0, which means the derivative will be 0. However, if the tangent drawn is vertical, then we'll say that the slope of the vertical line is undefined, and we know the reason why. So remember that slope is a rise over run. And you can rise as much as you want here, but we don't have to run. We run nowhere on a vertical line, which means that we have to divide the rise by a 0, which is undefined. That's what makes the slope undefined. So we're going to say that if the tangent drawn on a graph is vertical, it means that the slope of the tangent is immeasurable, which means again that the derivative of the function doesn't exist. So we're going to say the second scenario where a function is non-differentiable is if the tangent has immeasurable slope, or if the tangent line is vertical. So what we are going to look at is a third scenario, which I didn't list in here, but the number 3 scenario is when we can draw more than a tangent at a point, or if a point can have more than 2 rates of change, more than 2 derivatives. And as an example, I will bring in here the graph of y equals absolute value of x. If we were to measure the rate of change at this particular point, which in calculus we call them corners, so 2 straight lines connected to each other, then at this very point, we wouldn't know if the rate of change would be that of this part of the graph or that of this part of the graph. So when we are undecisive whether or not we have to use one or the other value because 2 different values exist for the derivative of the function at this point, then we're going to say that the derivative is undefined and the function is non-differentiable. Similar to corners, we also discuss these unique shapes that we call cusps. Cusps are again corners, but they are created by 2 curved lines instead of 2 straight lines. So in the next section of this lesson, we are going to take a look at some examples where we will illustrate all the different cases that we mentioned when explaining differentiability.